welcome back. Last time we talked about network of queues, and of course we would like to model each of the queues in a big network as an NM1 queue because that is the simplest thing we can model. But as we discussed last time, even if like each of the tiny link in the system have only one single queue, let's say the server, also like behave in a way that it just um, kind of normally, in the sense that like it will spend time kind of proportional to the length of the packet, considering this is a computer network. Then we already get into a trouble that even we have a very simple system with two links, the second system cannot be modeled precisely using an MM1 queue. But of course we can still do that. It will then only be an approximation, and actually that is referred to as the hierarchy independence assumption. Today I'd like to go into a little bit more technical. I want to discuss a theorem known as the Jacksons Theorem. What the Jacksons Theorem says is that the occupants of all links in the system can be modeled by independent MM1 queues. That is, for each link in the system, the probability of the number of packets equal to n is just equal to rho to the n times 1 minus rho. And rho here is just lambda over mu as usual. And this holds if the following conditions are satisfied. Basically, the traffics are routed randomly at each node. So like this one here, each node, when there's packets coming in, it may route to here, and so on and so forth. Is, of course, we don't have something completely random, but this probably is pretty good approximation, good assumption for a normal network. And the second one is that the departure time, or like we can think of the service time, should be random. So therefore, like it's supposedly it should be kind of independent of the packet length. So this is exactly why we see the example we have given last time break this assumption, and therefore like the Jacksons theorem does not hold well in those cases. The proof of the theorem itself is rather involved. So what I'm going to do is just trying to give an example that will hopefully will give some intuition why this theorem will hold. So let's say we have a system like this, that we have a traffic going into a node, server node, and the output of the traffic from the node, that will be a probability P that will got feedback and feedback to the system again. So if you look at that, like ignoring the feedback here, as a whole here, that there's a system. Another we can think of this itself is a system, and so if this system is kind of steady state, eventually the weight going out of this system has to be equal to the weight going into the system. Therefore, going out here is lambda, and since like that's p probability going to have feedback, that's 1 minus p probability that is going out. So therefore the traffic going out of here should be lambda over 1 minus p. So therefore going this way should be lambda p over 1 minus p. And we can verify that this lambda p over 1 minus p plus lambda is equal to lambda p 1 minus p plus 1 minus p, that is equal to lambda 1 minus p. So okay, this matches also. Here, just trying to compute all this like appropriate traffic going into each of these paths here. And now what I want to say is that for a system like that, it's not likely to be MM1, or like it can be MM1. we can model this server node using MM1 correctly, accurately, because the traffic itself going into this node here will not be Poisson. Why it will not be Poisson is rather reasonable, because if we think of there's the P is pretty big, let's say P is close to 1, then what happens is let's say lambda is rather small, less than 1. We're likely to have a burst traffic going into here, into this server node here, because whenever we have one traffic going in, it's just going to feedback a couple of times. So something like, if there's a traffic here, okay, it's going to feedback several times, and then for a long period of time, there's nothing going on, there's traffic here, there's a couple feedback, and so on and so forth. And remember that the assumption to have a Poisson process is that there should be low correlation for the number of arrival within a period relative to another period, but apparently this independence is basically broken in this case here. Okay, now what I'm going to do is I will just, at each point here, I will denote A, B, C, and also in this link going backward here, I'll just assume that that's going to have a very tiny delay, delta. This can be very small delta here, and this backward kind of feedback link, I will just call it D here, this E here, and with some abuse of notation, I'll just call A0 as the first of all, I guess I need to mention that I'm going to kind of partition the time axis with tiny delta, as we did previously, but this delta will be equal to this delta here, and I will just say A0 as the traffic at the first time slot here, and B0 as the traffic at this time slot here, and B1 will be the traffic for this time slot here, and so on and so forth. So at the beginning, you can imagine that there's first no traffic here, so A is just equal to B. We have a Poisson traffic going from going right across. We have B0 is basically just equal to A0 here, and let's say this is just Poisson going in, or I should put it here, maybe A0 is just Poisson going in into this node here. Let's say it just have one queue, and let's say the service time is kind of random. So in the sense, it will add at that instance, MM1 queue, and the output here, see here, will be just Poisson also. Basically, C0 is Poisson. And this is because the burst theorem that we discussed last time, burst A basically, that because for that short time instance, this system is time reversible, therefore the departure statistics would be just equal, it will be Poisson, and also the departure rate will be just equal to the arrival rate. And so this C here will split into this D here, and this D0, because it's randomly splitting here with probability, some probability, therefore this traffic D0 will also be Poisson. So I have something Poisson also. And and this E here, because of this tire delay, this E0 is, or I should say E1 should really equal to D0 here, and this will be Poisson also. Now let's look at the next time instant, B1 here. The first time instant, we see that this effectively an MM1 queue, with the state that so So therefore, the occupancy should be distributed according to the MM1 queue. So for the next time instant, let's say I have B1 here, which is basically A1 plus E1. And of course, like this is Poisson and this is Poisson, the addition will be just Poisson. So we can say that, okay, because of that, this guy will behave like a Poisson or MM1Q also, but we need to be careful that it's true only when this incoming traffic is independent of the state of the system. So at the initially, it's reasonable that to assume that this incoming traffic has no way to do with the state of the system, therefore should be independent of the system. Therefore, in the first time slot, it's okay. But the second time slot, because we have this feedback, so intuitively, this traffic B1 may not be independent of the state. But luckily, notice this E1 is basically D0, and we are talking about the traffic D0 here, and we are talking about state at time here. This is the stop 1 here. Let's say this state is called S here, just whatever, some notation here. And remember, we have the Burke's 2 theorem, Burke's B, that's saying that the occupancy of the system is independent of the departure prior to what you're measuring at the moment. So therefore, like this S1 here will be independent of this D0. So S1 independent of D0, that is therefore S1 independent of E1. So therefore, like we have this B1 here will be independent of the occupancy at the moment also. Therefore, this outgoing, therefore effectively we can consider this as a MM1Q also. This outgoing traffic will be Poisson also, and we can say this D1. So C1 is Poisson. That's basically this time again by Burke's A, and then D1 is Poisson because it's just splitting it, and then we have like E2 is D1, is also Poisson, and so on and so forth. So we can continue to do that, and this for this tiny instantaneous moment, each of this delta slot, we can claim that like there is always Poisson, and so therefore like the occupancy will also be Poisson distributed. Okay, let me quickly go through a numerical example using the Jacksons Theorem. So let's say we are considering a computer system with a feedback loop. That okay, we have this lambda going in, then we have CPU, that I have this processing rate as mu1, and then like there's a chance that you're going to feedback this program needs to continue to process with the CPU, but first we need to go through this some I/O, and that's with a probability that P2 going to feedback, let's say, and the surface rate of this I/O is mu2, let's say. Typically, of course, this surface rate for the CPU will be much bigger than the surface rate of the I/O, in the sense the CPU it will be much faster. And so we can just write down the, okay, just denote the usual notation that let's say rho1 is equal to lambda 1 over mu1, and rho2 is lambda 2 over mu2, and lambda 1 is just the traffic getting into the CPU, and lambda 2 is traffic getting into the I/O. And okay, we can compute how this lambda and related, because we have lambda 1, lambda 2, and lambda related. We have basically probability P2 going out of this CPU feedback to this I/O. So the traffic going into the CPU is lambda 1, I'm sorry. And I mean this going out is lambda 1, therefore lambda 2 is is equal to P2 times lambda 1. That's here. And also, of course, like lambda 1 is the traffic that getting in and also the feedback traffic. So therefore, lambda 1 is equal to lambda plus lambda 2. And from that, we can compute lambda 1 and lambda 2 as this here, represent lambda 1, lambda 2 by this here. And by Jacksons theorem, we think of like the overall occupancy of this system will be just equal to, because each of these occupancy will be just behave like an MM1Q. So therefore, the overall occupancy for probability that first the CPU have M1 packet, or like whatever you can think of like byte in the system, and let's say with N2 packets in the I/O will be just ρ1 to the power N1 times 1 minus ρ1 times ρ2 to the N2 1 minus ρ2. And then like the average, therefore we can compute the average number of packets in the entire system. I mean, it will be very easy. It's just basically is like PM1 N2. This big N should be just times M1 times N2, sum over M1, N2, and so on. And if we solve that, we have N is just equal to this here. And so therefore, like we can use the Little's theorem that the delay in this system here, we think of this traffic getting into here until it getting out here, will be just equal to N over lambda is equal to this expression here. Okay, we can continue to simplify the expression. Eventually, we will get something like this. It's equal to 1 over P1 mu1 minus lambda plus 1 over P1 mu2 over P2 minus lambda. And if we look at this expression here, this is okay. This each of this delay here is like a delay of an MM1Q, average delay of an MM1Q, with the corresponding mu equal to this, maybe you erase that, with the corresponding mu equal to P1 mu1 and P1 mu2 over P2. Or we can think of like with the corresponding surface time, average surface time to be 1 over P1 mu1 and P2 over P1 mu2. So therefore, like we can draw an equivalent system that have the same average delay as this model here, with 1 lambda here, and we have this the surface rate of the first system is P1 mu1, and the surface rate of the second system is P1 over P2 mu2. Okay, the average delay of this system will be identical to the average delay of this original system. However, the actual statistics, the delay statistics will be very different. I mean, the delay distribution for this one will be quite uniform, right? Because if you think of that, like you always need to go through this and then go through that. But for the original system, actually the delay will be very much not uniform, because especially if we consider this surface rate for this I/O is much smaller, it will take much longer time to process this feedback. So if a packet that go through without the feedback will have a very short delay, but if it need to feedback, it will have a much longer delay. So therefore, for this one, we'll have a delay distribution is very much spread, and this one will be like kind of like level, and that's all.